This movie we'd like to talk about gears and gear ratios. It's kind of similar to simple machines, but there's a little bit difference. In simple machines, you had a trade-off between distance and force. In gears, you have a trade-off, but it's a trade-off of a couple different things, and we'll look at here in a second. So what is a gear? A gear is basically a wheel that has these teeth on the edges, and then one gear is meshed with another gear. And as one gear turns, for instance, this red gear over here, as it turns around this way, it applies a force onto the blue one, and so then the blue gear turns the opposite way. So two meshed gears, if one's traveling counterclockwise, the other one then will be traveling clockwise. And if you notice these gears, there's a little difference between them. This red gear has an N, which is the number of teeth of 6, and the blue gear has an N of 12. And what's important in determining gear ratios is you have to figure out which one, or you have to be told which one is the driving gear and which one is the driven gear. So in this case, the red one we're going to say is our driving gear. This red gear is probably hooked up to some axle, hooked up to a motor, and the motor's turning and spinning this gear. So this red gear is the driver, and therefore the blue gear is the driven gear. And that's important because this is how we're going to kind of determine gear ratios. Another term for driven you might see is out, and the driver is in. This is where you're putting the effort force in, and then the other one is the force is coming out. So driven and driver, or out and in. And a gear ratio is your driven over the driver, or the drive. The driven over the drive. Or sometimes we write the ratio like something like this. So the driven, I guess I should keep that consistent, the driven ratio to the drive. Driven ratio drive. Okay, so there are several things that you can actually use to figure out this ratio. One thing you might be able to use is the actual diameter of the wheels or the gears. And so you'll notice here the diameter of this blue gear is 4 something inches, we'll say, and the diameter of the red one is 2 inches. 2 inches. So the gear ratio of the driven to the driver is 4 to 2, or you could simplify that to 2 to 1. That is your gear ratio for this particular these two gears. What's another way you can figure out? You could use teeth. So I'll just write some equations here. First of all, I did diameter of the out over the diameter of the in. That's one way. I could do number of teeth, N, of the out over number of teeth of the in. And you'll notice here this blue has 12 teeth and the red has 6 teeth. So that again is 2 to 1. 2 to 1. Driver, or the driven to the driver. So that's one way. Another way you can do this is if this red one is turning fast at 40 RPM, or rotations per minute, 40 rotations per minute, then this blue one here, the best way to do this is kind of see this in action, is to actually turn the red one and watch what happens to the blue one. This red one will only turn 20 rotations per minute. So this red one here will turn or spin around twice in the same amount of time that the blue one spins around once. And if you watch the teeth go around through there, you'll see that that's the case. So the red one would go around twice every time the blue one went around once. Now, that, though, is backwards from these other. All these other ones were out over in. So this one, rotations per minute is a velocity, but it's a rotational velocity. So we don't use v. V is like a linear velocity. We actually use like an omega symbol. And in this case, then, it will be in over out. So the rotational velocity in over the rotational velocity out, in this case, would be 40 over 20, which, of course, is still 2 to 1. So we could use rotational velocities also. Whenever you have a gear system like this, the smaller gear is going to have the more rotations per minute than the bigger gear. So you're going to get more velocity out of the smaller gear than you are out of the bigger gear. The other thing we could look at that actually isn't on here is called torque. And torque is the amount of force times basically the distance or the radius of this wheel. So you have a certain amount of force times this distance here, and that would be a certain amount of torque. We'll call that torque in. And then the force doesn't change. That whatever force these teeth are coming around and hitting this tooth here, that force would just be exchanged onto this new tooth. So the force would still be the same around the edge of this blue wheel, but this has a bigger radius, right? So if you have the exact same amount of force times a bigger radius, remember torque is the force times the radius. If I have the same amount of force, but this is a bigger radius, then that would mean more torque around this one, and less torque around this one. So your torque in is going to be small on the small wheel, and the torque out is going to be big on the bigger wheel. And so we don't have any torques written down here, but you can probably imagine that another ratio is torque out over torque in, and whatever that would be, it'd still be 2 to 1. So there's 4 things here that 4 different equations that we can use in a gear system like this to figure out the gear ratio. The gear ratio can be the diameter out over the diameter in. It could be the number of teeth out over the number of teeth in. It could also be the torque out over the torque in, we'll say. Or it could be equal to, and this is the weird one, it'll be the reverse. It'll be the rotational velocity in over the rotational velocity out. Those are the gear ratios. So what does the gear ratio tell us? Really, if you remember in simple machines, it was a trade-off of distance and force. So if you applied a force over a very long, high distance, then you could apply a very small force. So there was a trade-off. So you could lift a really big force as long as you were willing to put in a very big distance into the system, or put a small force in for a long distance, then you could lift a big force. So simple machines are a trade-off between distance and force. Gears are a trade-off between torque and rotational velocity. So if you look down here on this one, the blue gear would have high amount of torque, but it has a small rotational velocity. It doesn't go around very fast. The red gear, on the other hand, has a small amount of torque, but it goes around very fast. So you'd have a small amount of torque, but you'd have a nice high angular velocity. For the blue one, you'd have a large amount of torque, but you'd have a small angular velocity. And this is what you're deciding between on these 2 things, on what you want. We'll talk about that more when we talk about like bicycles and stuff. So here's all of your equations, possible things you could use for gear ratio depending on what they give you in a problem. The easiest one is always really the teeth. or the diameter. So you got to remember, though, it's out over in for all three of these except for the angular velocity. It'd be the angular velocity in over the angular velocity out. Okay, and of course, if the driven is bigger, then all of these gear ratios are going to be greater than 1. You could go the other way. If I could say in this problem the blue gear was the driver and the red one is then being driven. And that's totally fine. You'd still use all the same gear ratio equations, but now since we're doing out over in like normal, your out is this one and your in is this one, so you're going to have less than 1 gear ratios. So gear ratios greater than 1 means that you're multiplying your torque. You're going from a small to a big, and that means your torque is increasing. You're putting in a small amount of torque and getting a big amount of torque. That also means you're putting in a high amount of RPMs, and you're going slower up here. Okay, so let's before we finish this one, let's look at another situation here. Let's say we have a bigger gear system where we have some gears in between. These gears in between the main gear and the last gear are called idler gears. Those two gears would be idler gears. And what happens here is, let's say that gear A is moving this way, which would be counterclockwise. That means gear B then is going to move clockwise, which would mean gear C is going to move counterclockwise, and then gear D then would be moving clockwise. So if you just had one gear in between there, if you have one idler gear, then like let's say that D wasn't even there, D didn't exist, then gear A would be going counterclockwise, and so would gear C. So sometimes if you want but two gears to be going the exact same direction, you put an idler gear between them. So we have two gears. If we have an even number of idler gears, then gear A and gear D will be going opposite directions, just like as if they were attached to each other. So let's look at gear ratios here, starting with A and B. What is the gear ratio of A and B? Well, A is the drive, and B is the driven. So if we just do it with teeth, it'd be the driven. So A and B, and then we'll look at B and C, and then we'll look at C and D, and then we'll look at what A was all the way to D, pretending the two idler gears weren't even there. Okay, so we're going to go to A to B, and that's the driven, which is 12, over the drive, which is 20. Take 12 divided by 20, and I get a gear ratio of 0.6. Now what does that mean? Does that mean we're going to get more torque? No, it means we're going to actually get more speed. So we're going from a big gear A to a smaller gear B, which means we're going to increase our RPMs. It's going to go rotate faster, but I'm losing my torque. Okay, now I'm going to go from B to C. So C is the driven. That's going to be 5 over 12. Take 5 divided by 12, and I get basically like 0.42. 0.42. 5 divided by 12. About, 0.42. Okay, and that would mean that I'm still not gaining torque. I'm still gaining some faster speed. So this gear would be going spinning around even faster. All right, C to D. I'm going to have 20 over 5, and I get a gear ratio of 4. Okay, that's a greater than 1. That means I'm really going to multiply my torque. So this gear D is going to be going a lot slower than gear C is. In fact, it'd be going 4 times slower because the gear ratio is 4. I'd be going 4 times slower than what gear C is going to be going, but I get 4 times the amount of torque or crank out of it. Okay? All right. So how do I figure out what the gear ratio of this whole system is? I have gear A to B and B to C and C to D. I can multiply all 3 of those together. I multiply them all to get an overall gear ratio of A all the way to D. And if I do that, if I take 0.6 times 0.42 times 4, I get a gear ratio of, drum roll please, 1. If I multiply all three of these, I get a gear ratio of 1, which is really interesting because what if I just took the idler gears out and I just attached A to D? Well, they both have 20 teeth, so it would be 20 over 20, and the gear ratio would be 1. So what point did the idler gears do for us? In fact, they did nothing. They did really nothing. Idler gears don't do anything for the overall gear system. Why would you put them in there then? There's only two reasons to put the idler gears in. Number one is your gear A might physically have to be here and your gear D might have to physically be a long ways away. And so to get gear D to turn, you would actually have to put some idler gears in there physically to get gear D to turn because of gear A. So they're just spacers to convey the force over to gear D. That's one reason. The other reason, you might want to have gear D spinning a different maybe the same way. Now that's not going to work in this situation because you have an even number of idler gears in there. So gear A, if it's going this way, counterclockwise, gear D is going clockwise, so they're going opposite. But if you put one idler gear in there, you had maybe a little bigger gear in there that could span that whole distance from here to here, then you might want to do that because you might just want both of these gears to be spinning the same way. If I put one idler gear in here, then this would be going this way, and this one also would be going this way. And so the purpose of the idler gears is going to be to either physically transfer the force from the first gear, from your drive gear, all the way over to your driven gear, or it's to make your drive gear and your driven gear perhaps rotate in the same direction. You might want that to have happen or something. So technically this is the drive and this one is your driven, and everything else in there doesn't really matter. That's idle gears or idler gears.